Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet to be published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the webinar series with academics of the ITU Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open today the webinar with Professor Akan, University of Cambridge, UK. Please submit your question via the Q&A channel. We will address them to our speaker during the Q&A session. And after the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live life lessons. So please stay online. Professor Akan agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm pleased to introduce Professor Ian Akilditz, Editor-in-Chief of the ITU Journal and founder and president of TRUVA from the United States. Professor Akilditz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. Professor Akilditz established many research centers worldwide, including South Africa, Spain, Saudi Arabia, and Finland. He's Editor-in-Chief Emeritus of Impact Factor journals, highly cited and at the top of the most prestigious international rankings, visiting distinguished professors in many universities around the world. And his current research interests are in 6G wireless systems, terahertz communication, metaverse, communication in challenge environments, and many others. Professor Akilditz, the floor is yours. Thank you.
Thank you, Alessia. Our distinguished guests, esteemed colleagues, and honored participants, good morning, good afternoon, and good evening, wherever you are joining us from across the globe. From the historic city of Istanbul, a timeless bridge between continents and cultures, it is with immense pride that I extend a warm welcome as we inaugurate Season 4, Episode 6 of the ITU Journal on Future and Evolving Technologies, in short form ITU JFAT webinar series. Today, we are privileged to host an extraordinary mind, Professor Özgür Akan, a visionary whose pioneering work is reshaping the frontiers of nanoscale communications, Internet of Bio-Nano Things, and next-generation wireless systems. Before we proceed, allow me to reflect on the transformative mission of the ITU Journal. Since its inception in December 2020, this journal has stood as a beacon of open access innovation, relentlessly bridging academia and industry while accelerating the democratization of cutting-edge research. Every submission undergoes rigorous peer review, ensuring that only the most impactful, forward-thinking contributions shape our technological future. Our journal's rapid ascent as a premier global publication owes much to an exceptional team: Sizo Ono-san, Bilal Jamusi, Alessia Magliarditi, Enrique Campilongo, Mario Otero, and many others whose dedication has been nothing short of extraordinary. To our global audience of researchers and innovators, we invite you to contribute your breakthroughs and papers and help us drive the next wave of discovery. I'm also delighted to announce that our journal has been officially indexed in the DOAJ, Director of Open Access Journals, a milestone that amplifies our global reach and reinforces our commitment to unrestricted knowledge dissemination. Now, it is with immense pride and profound admiration that I introduce today's distinguished speaker, a visionary scholar, trailblazing researcher, and cherished colleague, Professor Özgür Akan. Professor Özgür Akan stands among the foremost pioneers in the field of communications, with transformative contributions spanning nanoscale and molecular communication, next-generation wireless networks, 5G and 6G, the Internet of Bio-Nano Things, and neural interfaces. His work transcends conventional boundaries, merging engineering with biology to forge revolutionary advancements in medical and technological systems. Özgür earned his PhD from my research lab, Broadband Wireless Networking Lab, School of Electrical and Computer Engineering at Georgia Tech, 21 years ago, 2004. Today, he holds dual prestigious appointments. One is the head of the Internet of Everything group at the University of Cambridge. As you know, this is maybe the top university in the world, where he leads the bioelectronic systems group in the Department of Engineering. And another one is AXA, or AXA Chair Professor in Internet of Everything and Director of the Center for Next Generation Communications at Koç University, Istanbul, Turkey. He is a fellow of the IEEE. He is a Turing Fellow, Royal Academy of Engineering Chair in Emerging Technologies, and recipient of the prestigious ERC Consolidator Grant. Professor Akan's scholarly impact is nothing short of extraordinary. With over 16,500 citations and an H-index of 64, his research has redefined paradigms in communication theory and nanobiotechnologies. His further accolades include TÜBİTAK, that's a Turkish NSF Science Award, that is Turkey's highest scientific honor, IEEE Komsak Outstanding Young Researcher Award, multiple IEEE Best Paper Awards and keynote distinctions, IBM Faculty Award, and he's also elected as IEEE Nanotechnology Council and Communications Society Distinguished Lecturer. He has served in serving as steering committee member for IEEE Infocom Conference, which is the top-notch networking conference from the IEEE Computer Society and IEEE Communication Society. He served as General Chair for IEEE Infocom 2017, ACM Mobicom, which is Mobile Communication Networks Conference for the ACM Society in 2012. And he also served as TPC Chair for numerous prestigious conferences. His editorial leadership is equally impressive, serving on the boards of IEEE transactions on molecular, biological, and multi-scale communications, scientific reports, Elsevier nanocommunication networks, and IEEE transaction communications, and IEEE transactions on vehicular technology, among many others. Now, personal opinion, my personal feelings. Beyond his monumental academic achievements, I have had the exceptional privilege of knowing Özgür, or Professor Akan, not only as a luminary in our field, but as an extraordinary individual. When he joined my research lab as a PhD student in January 2002, is almost like 23 and a half years ago, his brilliance was evident from the outset, a rare combination of sharp intellect, relentless ambition, especially ambition, and unwavering dedication. Our collaboration flourished into groundbreaking research in wireless sensor networks, communication protocols, 3G. Can you imagine? Now we are talking about 6G. We worked on 3G resource allocation in mobile wireless systems. This work, or this cooperation, led to seminal publications that continue to influence the field. Yet beyond academia, what truly distinguishes Özgür is his character. He's a person of unshakable integrity, profound professionalism, and remarkable resilience, qualities that have propelled him to the zenith of his discipline. Our bond, forged through countless day-night and discussions, collaborative breakthroughs, and cherished moments, whether over dinners along the Bosporus, spirited soccer matches, or travels across the continents has evolved into a father-son relationship that I deeply treasure. Today, as he stands at the forefront of bio-inspired communications, pioneering molecular data transmission, neural communication models, and nanoscale sensing networks, his work promises to redefine the future of medicine, connectivity, and human-machine symbiosis. Dear Özgür, we are truly honored by your presence today. Your insights will undoubtedly inspire and enlighten us all. Ladies and gentlemen, please join me in giving a warm welcome to Professor Özgür Akar. Thank you, Özgür.
Thank you very much, Professor Akyildiz, and to the entire ITU Journal for this kind invitation. But I'm truly humbled and shocked for the introduction that you have done, Professor Akyildiz. Thank you so much. Thank you. I'm honored. So thank you very much to the entire audience who have taken up their time and joining this webinar. This is an excellent webinar series. And I'm honored to be the first one for this fourth season. So let me share my screen meanwhile. And I do apologize for my terrible voice today because I got cold in the colds of Cambridge. So today I'll talk about the very broad vision of Internet of Everything. And as the title says, from molecules to the universe. I'm not going to go into details of any of the papers, but I'll be happy to discuss if you have any question either during the presentation or at the end. I'll provide the references under every slide if you want to go deep. But my intention is to give you the several flavors of what's happening in the frontiers of communication technologies in the very small scale up to literally interstellar scale or galactic scale. And I'll be talking about some crazy stuff, so don't shoot the messenger. Some of the names we haven't coined, but we're trying to catch up with the research. So this is basically, in a nutshell, the evolution of communication technologies. Let me get my laser pointer. I hope that it will be helpful. So we are starting from this before Christ, 40,000 years, where we have been drawing images on the walls of the caves to communicate. Then using smokes. This might be familiar to you. This is after the Christ. This is the pigeons or the ravens, as in the Game of Thrones. This is the optical telegraph. I wish I had a time to go into details of all of these because there are very interesting stories behind every piece of communication technology. Fast forward, some of these might be already familiar to you. The internet was born around 1969. And then fast forward, in the last couple decades, we've been working on, as Professor Akyildiz just mentioned, as in my PhD as well, we were working on new technologies like sensor networks. Then it was called machine-to-machine communications. Now we're using cloud computing in the software sense. And currently, the generation of wireless systems that we're using is called 5G. All these have led up to the establishment or emergence of what is called as Internet of Things. But again, don't forget, the title of my talk is Internet of Everything, not Internet of Things. And I'm going to explain what is the difference between the things versus everything and the Internet in the IoT versus IoE. So what is the Internet of Things in the classical sense? That is the network of physical objects or things embedded with electronics, software, and sensors. So this is already a well-established field. Basically, what's happening in any IoT infrastructure, there are devices and sensors which collect the data. Data is communicated through the network, and information is extracted from the data, and there's some action to be taken on the field where the sensors or devices are deployed. This has tons of applications in various domains like transport, logistics, smart cities, environment, agriculture, etc., which I'm not going to go into details. If we look into the broader view of what's happening in the IoT landscape, what we can see is in the IoT market, so this plot on the left-hand side left top corner is by McKinsey. So the economic impact that was expected this year, which has already surpassed, is in the order of several $trillion. And the top leading field is the industrial IoT. So Internet of Industrial Things, or Industrial Internet of Things, basically has applications in the factories, premises, and automation, etc. And there are other venues as well. Obviously, there are other researches or expectations about the IoT market. We're talking about several, in the orders of $1 trillion. So this is the broader world. This is the US. As you can see, the numbers are consistent. But if we come back to our domain, basically research, so what you see here on the left bottom plot is the number of publications. So the y-axis is the number over the years. This is from Web of Science. And the number of publications with the IoT as its keyword inside has already saturated, which means that, of course, there are different aspects of IoT still being researched, but the IoT itself is becoming, kind of obsolete, despite we have tons of venues in terms of like journals and conferences and word forums, etc. So what is happening then? Where will it lead us? What is emerging? So this is what happened so far. And what's going to happen, or what is next, is beyond what has happened so far in terms of many dimensions. So obviously, we've been talking about the field of Internet of Nano Things, Internet of Bio-Nano Things, which was pioneered by Professor Akyildiz. And there are other fields within the context of Internet of Things, as you can say at the beginning, because it sounds similar, like Internet of Senses, brains, and other communication modalities like neutrino networks or gravitational networks. What the heck are they, right? I'm going to talk about them. And this brings us to another vision of what could be called as Internet of Everything. I'm going to define what it is, but let's see what it could be. The universe, actually, in which we are existing, right? We are interacting with all the entities through our senses and through our thought processes. We're trying to interact, and ultimately we try to control either by ourselves or with the devices that we generate, right? And communication is basically done for this purpose, right? Our machines, our computers, or phones are communicating, etc., etc. So this is fine as long as the entities are artificial devices. But how about if you want to modulate the behavior of certain planets, or if you want to interact with certain planetary bodies? In fact, many researchers before us, like Da Vinci and Wheeler, you may know Wheeler, he was part of the Manhattan Project, and he was also PhD advisor of Richard Feynman, which we will also refer to in a minute. So they all observed and identified this relation. Basically, everything is kind of information, and everything is connected to everything else, one way or another. So if we lay this down on fundamental physics, mass can be converted to energy and vice versa, which we know that both theoretically and experimentally. And energy also can be converted to data, which is obvious, but data or information can be converted to energy, which may not be obvious, but can be considered as part of, observed as part of the Szilard's engine thought experiment. Basically, the summary of this experiment is as follows. If you know the exact location of a single molecule in a chamber over time, then you can utilize such a small mechanical device to harvest energy out of this information. And there are physicists trying to experimentally realize this. So what am I trying to say here? Basically, everything around us is a data source, and data is everywhere. And communication is not just for WhatsApp or 5G, 6G, etc. Communication is at the core of almost every complex phenomena, like evolution, intelligence, memory, and consciousness. Okay. So let me give some proper examples to that. Like there is a field growing. I'm going to talk about some part of it, like within the context of Internet of Bio-Nano Things, but there's a field or subfields growing under the names of Internet of Genes, Cells, Tissues, or Organs, overall giving rise to living organisms. And as you can see, these entities like genes, cells, tissues cannot be really thoughts exactly the same with the things in the Internet of Things, because they're not silicon-based devices with software embedded, right? But they have certain input-output relations. On the other hand, the Internet in the context of Internet of Genes or cells, etc., are not the same Internet, because in the classical Internet, what we're using is the optical fiber links for the backbone and the wireless for the last mile, right? But here, the modality is different. What is that? That is molecular communications or molecular and electrochemical communications. So another Internet of X, Y, Z, whatever you want to call is Internet of Plants. We'll talk about that. Again, don't shoot the messenger. It's called Wood Wide Web, giving rise to biosphere with different modalities. There is an ongoing research. I've referred some papers here. Please feel free to dig into by some other researchers. Quantum communication might be among the microtubules between the neurons inside our brains. So the computations in the brain may not be really just conventional. Quantum entanglement might be also there. Another communication modality, which is existing in the universe, is through gravitational wave, which we will also talk about it. So how can we name them? Are they part of Internet of Things? Are they part of the current Internet? Or the things here that I mentioned, same with the silicon-based things? Obviously not. So what we talk about here is a vision, as I told you at the beginning, and this vision is referring to the universe as the Internet of Everything. We're just interested in some part of the universe, obviously. We're interested in interacting with, and we're trying to devise communication technologies to realize that. So these are the modalities we have, we meaning the entire human being, our species, have come up with so far, like acoustic, visual, mechanical, or horsepower, right? Like Mancio Posita, postal network, resting places in the Roman Empire. Optical, telegraph, again, visual, then electrical, wow, then electrical acoustic, then electromagnetic, wow. It's like granted for the time being, but it's been just 100 years only. We've started to use electromagnetics, then optics, another kind of EM. What else, right? Quantum, yeah, we haven't started to use it as a last mile consumers. What else? Gravitational, don't know. Molecular, yeah, our bodies use, but not us. So these are different modalities that will be part of the Internet eventually. Hence, the everything is also different than the thing. So what is the difference here? Now, when we say Internet of Everything, we're referring to all the things that are in the universe, and we are interested in interacting with, either directly or between those entities. And the Internet for that won't be just wireless, RF, and optical, and it needs to incorporate new communication modalities, which is studied and researched by many researchers, including yourself. So this is the overall landscape of Internet of Everything, which has many X and Ys. Some of them are quite conventional, and we are very familiar with them, like Internet of Vehicles, right? Or industrial IoT. Or Internet of Agricultural Things, which has some interesting stuff as well I'm going to talk about, or Internet of Space. But some are quite new, like Internet of Energy or Internet of Money, Internet of People and Senses, and Internet of Nano Things. I'm not going to go into details of many of those, like money, energy, etc. But I have a course here in Cambridge on Internet of Everything that I discuss all of these in several hours. But here we don't have much time. So what are the challenges? When we want to interact with all these heterogeneous entities, of course, there are tons of challenges, right? Some, again, classical, like connectivity, bandwidth, energy efficiency, etc. I'm not going to touch on them, but miniaturization, right? we need to get things smaller. And interoperability, we need to have various types of interfaces. So that's very important. Of course, security and privacy. When we interact with like cells and tissues or organs of human being, security and privacy is a very understated and unfortunately understudied domain. Of course, there are tons of challenges, but there are also nice progresses in certain key enablers directions. So how do we overcome these challenges? Of course, with electronics, right? So, the Moore's law, every couple of years, the number of transistors packed in a unit area is doubling. That's fine. It's going to saturate, hasn't saturated yet. We are around few nanometers in terms of the scale of an IC, of the gate, let's say, of a transistor. But what is emerging is called as more than Moore instead of more Moore. Basically, not just increasing the density of the IC, as in this y-axis, but the functionality of any electronic device. So instead of having just computation, having both analog and RF electronics packed together, passive sensing, high voltage power, or harvesting as well, sensing and actuating, and biochips or bioelectronics. So this is an enabler required for IoE. Of course, along these lines, microelectromechanical systems and nanotechnology with different materials at the forefront, graphene and graphene-related materials, very useful. I'll touch upon that. Flexible, variable, printable things for various sensing modalities. By the way, these are all existing in the research domain. These are not science fiction, obviously, but they need to come together. Medical micro-nanorobotics, organic neuromorphic devices, basically mimicking the neuroplasticity and neurocomputation in the electronic circuits, and ultimately implementing or being able to implement artificial intelligence fundamentals or machine learning fundamentals in the memristor-based devices. So I promise this is the most that I'll talk about machine learning or AI in this talk. I'm not going to go into that field. So another enabler, of course, which is at the core of this talk is molecular communication. So this guy, Richard Feynman, had stated in his Nobel Prize speech that there's a plenty of room at the bottom, referring to the nanoscale regime. And the question we were asking is whether the room down there is sufficient for a communication network. And the answer is yes. So this guy, again, student of Wheeler that I referred to at the beginning, opened or paved the way for designing and implementing small-scale devices that you can see some illustrations here. Like here you have bacterial nanotube networks or nanoparticle communication networks, which may release certain drugs after detecting certain chemical substances released by tumors in the blood vessel. Then the answer to this question has led us, many researchers, of course, pioneered by Professor Akyıldız and many others around the world, to work on this field, molecular communication, to come up with theories, devices, simulators, and experimental testbeds. So the idea here is that this is an abstract molecular transmitter, and this is a receiver. The medium might be aqueous medium, or might be airborne, and some other environments as well. So this transmitter here releases certain particles, okay? They could be called as information molecule or ligands, and they might be subject to diffusion only following the gradient, or plus diffusion plus drift, certain electromechanical or electrical or magnetic forces. And then once the sufficient amount of the ligands are bound by the receptors at the receiver, then the transaction of the symbol is successful, right? So this is the molecular communication basics. But of course, there are tons of different versions of that happening right now in the nature. As we speak, as I talk, and as you listen to, this is happening in our bodies. From this abstract view, now we are able to actually fabricate and characterize transmitters and receivers for this field. So one example was we've been working on this theoretical molecular radio, so to say, with first-order resonance energy transfer, which is a physical phenomenon discovered by Förster, and it is being used in the DNA measurement. So the idea is that when you excite this donor protein molecule, so this is a specific protein molecule, fluorescence protein molecule. When it is excited by an external laser, this guy releases a photon, which is not exciting. But if there is another acceptor protein in the vicinity of this donor protein, and if their oscillation spectra overlaps, like observed here, then in addition to this photon emission, a strange thing happens, which is a non-radiative energy transfer from donor to acceptor. Again, I repeat, non-radiative energy transfer. Why is it happening? We don't know. Don't ask me why. But we don't care as an engineer, because as long as there is an energy transfer, we can modulate it and send information. So that's what we have done, first theoretically, and then experimentally, we have realized the first molecular radio over this first-order resonance energy transfer phenomenon. For the time being, it doesn't have any use inside the Bio-Nano Things or Internet of Bio-Nano Things applications, which I'm going to elaborate now, because the excitation requires certain energy levels. If you embed this donor protein inside the body, excitation from outside is not sufficient for the time being, but once it could be done, then it may pave the way a lot of sensing and communication modalities within the context of Internet of Bio-Nano Things. But you can, for the time being, listen to certain music recordings like Bob Dylan's House of the Rising Sun or many others at this link, transmitted through protein molecules. So, Internet of Bio-Nano Things is a species within the context, within the broad umbrella of IoE, but it is not yet another IOX and Y. I believe it is at the center of the Internet of Everything. It could be referred to as Internet of Nano Things or Bio-Nano Things. So bio-nano does not necessarily mean that it should be bio and nano at the same time. You may consider it as a union instead of just intersection. And we're talking about nano machines or micro machines or biological entities together, fulfilling application requirements and have a representation in the internet. And this has been listed as one of the top 10 emerging technologies in 2016 by World Economic Forum. And it is since then emerging field, bit slowly, but it is extremely interdisciplinary. That is the reason. But there are very nice journals like the Nano Communications Networks Journal, Elsevier, which was again established, pioneered, created by Professor Ak-Yıldız, and there is an IEEE transactions in this field. So many applications and projects have been realized so far. I've included the codes of the projects. I assume many of them are still publicly available. If not, I'll be happy to share many of the knowledge that I have with you. So I'll talk about some of these, like this artificial synapse. I was a reviewer for this very nice project that basically implants multiple transceivers in the human heart. That is the objective, right? So that they can proactively detect the anomaly in the heart rhythm and then communicate among each other and then act accordingly, right? So there was this another project funded by NSF, led by a group of researchers, led by Professor Ak-Yıldız, bacteria-based molecular nanonetworks, where you inject the information into the nucleates of the bacteria and they tumble around, but eventually they deliver the message. So in this project funded by ERC, we have studied the nervous system Why? Because the nervous system is one of the most studied system inside the living organisms, and we had many experimental results, and we thought we can learn a lot to come up with engineering solutions for artificial small-scale devices, and ultimately perhaps solve some of the communication failures inside the body in the nervous system by applying ICT-inspired solutions. So we have received a lot of, we have obtained a lot of results. I will be happy to discuss many of these with you at the end if you like. We've modeled almost, not the entire nervous system, obviously, but almost all of the distinct types of the neurons which have experimental results in the literature using the ICT theories and validated our theoretical results. We have done some experimental work on the earthworms using in vivo data communication, first time ever, and published in Nature Scientific Reports. That was a very fun research. I can talk about the details later on. Right now, we are in the process of validating our results on the cultured neurons, hopefully with our colleagues in the University of Cambridge. We have actually designed, fabricated in the clean room, and characterized receivers and transceivers for molecular communications based on what we have learned in the models of the nervous system. So this was the first graphene BioFET field effect transistor-based receiver for nanoscale molecular communications. We have actually used DNA concentration-based modulated signal to be received by this fabricated receiver. So this is the actual view of the receiver in this let's say homemade integrated circuit, which you can see the details of the fabrication and the results, which was published in scientific reports a few years ago. Then in another project, we worked on this array structure of this neural interfaces for neurotreatment, basically for spinal cord injury. This is very difficult. We've done it with Professor Andrea Ferrari, who is the head of Cambridge Graphene Center. We have designed and obtained some experimental results, but the results are not satisfactory for the time being. We still are pursuing this research to improve the results so that ultimately they could be used for basically bypassing the injured portion of the spinal cord here so that the patch can receive the signal from the brain and pass it to the motor neuron so that the injury can be treated, not cured, but treated, right? In the funding by AXA, or funded by AXA in the project called MiFi, which is micro nanoscale transceivers for wireless molecular information communications, we tried to design and implement the first artificial liquid-borne and airborne molecular communication transceivers. And as an application domain, we targeted the artificial gut-brain axis testbed. We have done lots of modeling here in terms of the testbed, but we are in the process of, again, creating the testbed kind of this with the neural culture representing the or emulating the nervous system, or let's say brain, and the bacterial flora in another, let's say, a part in the experimental setup representing or emulating the gut environment, and then have a microfluidic channel in between, so that if we could observe the input applied here can be detected at the gut, or a piece modulating the gut, and vice versa, which would be a practical and low-cost experimental testbed to study gut-brain axis. Of course, this is nowhere near the entire gut-brain axis because it is extremely complicated. So we have very preliminary studies very recently. I think we have it here, right? Just published last year or 2 years ago, time flies, in ICC, and a new one on the short-chain fatty acid-driven vagus nerve signaling in the gut-brain axis in the transactions. But these are like water drops in the entire ocean. Because if we can all nail down the gut-brain axis communication, again, entirely different communication modality, right? I believe we can pave the way for development of diagnosis and treatment for various diseases, because what's happening there is very important, and that is a core research domain in the Internet of Bio-Nano Things. We have also realized during our research that we are calling this molecular communication as an enabler for Internet of Bio-Nano Things, which is the core at the Internet of Everything. But what really is molecule, right? So that was an interesting work. We've spent a lot of time on this. We had to read all the papers published. So at the time, so this paper was published in 2024, maybe submitted in around like summertime in 2023. So this plot here is the data from that time, 2023. So this is the number of papers that we have read. By no means this is the all papers in the field, right? But we have read with some filters, let's say some number of citations and venues. We have explained all this in the paper, but I don't recall that for the time being. But a representative sample, right? 1,500 is a representative sample. And out of this, almost half of the papers does not even specify what the molecule is in the molecular communication papers. And some numbers, some percentages use DNA, some calcium ions, magnetic nanoparticles, neurotransmitters, and other molecules, and other molecules, and other molecules. So basically, other and unspecified is the majority. But then when we go into physics of or physical properties of the particles, as you can see this illustration, I mean, from calcium ions to vesicles or magnetic nanoparticles, they're extremely different animals. When we come up with, channel models or transmitter receiver design and analysis, etc., for calcium ions, most probably it won't be valid for DNA or vesicles, which are the carriers of the neurotransmitters in the synaptic cleft. So that is an important catch that we need to be careful with. Then I think our field, now in hindsight, looking backwards, our field of molecular communications may have been misnamed at the time. At the time it was correct, but I think we could have called it as particle-based communications instead of molecular communications, because not necessarily all of these are molecules. We're talking about ions here, right? This is not a molecule by definition. Anyways, that's another discussion. We can come back to that later on. So within the context of particle-based communications, we have many frontiers like odor communications. Obviously, odor is part of our lives. We are using perfume and all, but we're not literally communicating with odor as human beings, but other organisms, other animals are. So it's important to learn how they're doing it and how we're also doing it in our olfactory system, because not only animals do it, but also plants do it among themselves. Plants do it with the animals and insects. And this is at the core of the agriculture. So this is very important for us to learn. So this is a growing field. At the end of the day, odor is a mixture of molecules. And the olfactory system and the senses here are basically the receivers for this type of a system. So it's important to have the channel model and analysis and understanding of the capabilities, and ultimately come up with transmitters and receivers for this communication modality. It may open tons of business applications as well. So we have designed some preliminary techniques trying to follow the main principles of odor. Like odor has certain perceptual dimensions by definition. If you go into the domain of odor or smell, it's really fascinating, by the way. You may remember there was a book and also movie, Perfume. So that's a very interesting word, So the dimensions are like pleasantness, intensity, and edibility. So some may sound familiar. Intensity also similar to magnitude of the signal, right? Edibility is a combination of certain dimensions which really hits to the perception of whether it is safe to consume or not. Pleasantness similar as well. You can remember some smells or odors. Basically, you might feel pleasant, or you might be repelled. So all these could be used to actually come up with certain modulation techniques to create waveform using odor signals. So now we have also developed a experimental test bed, and we're trying to get some results and hopefully share the results and publish it soon. So these were just theoretical and technique proposal ideas validated by simulations. Okay, I need to, I guess, a little bit fast forward. So many IOXs exist. So as we have just spoken with one of our senses, olfactory or sense of smell, basically, there is a ongoing field, again, don't shoot the messenger, which is called as Internet of Senses, People and Senses. Internet of Senses is very similar to wireless senses or wireless sensor network. So it's a bit old story. It's boring, I know. So I leave it aside. But Internet of People and Senses is interesting. So Internet of People is not really people using WhatsApp or Facebook, etc. It is through the senses. So we have 5 senses, right? So if you can replicate 5 senses of any human being at any point in space, then you might be actually replicating the entire universe, that person, that people observing at another point in the space, right? So what we've just discussed very briefly, odor, is relevant to that. So if we can have a receiver here detecting the smell in my room and send it over and replicate that smell, let's say in your premises, it might be a nice thing. Like if of course you might not be interested in how this room smells, but if you're talking with your friends or families, right, you may want to get their smell as well. But how about the sense of sight, like the eye? So there's an interesting project here by King's College London. It's called Internet of Silicon Retinas, and this was the first version. I think they've also received the funding, larger funding, for the continuation of this project. The idea was not just have a camera here, sorry, and capture the view and transmit, which is the toy project, right? But capture the stimulus at the retina or through the retina at the cortex and transmit that and replicate it at another human being. Of course, through a display, through an intelligent glass or whatnot. That's the easy part. But if you can replicate the sense, that is something big, right? So Neuralink, that you might be very well aware, is actually trying to do that, not through a sense of taste or smell, etc., is basically through the modality of the brain signals and what is stored there and how it interfaces with some surrounding entities. So this is an ongoing research field, and actually funded and promoted by some companies like Ericsson as well. I think one of your speakers in the past was our colleagues, Misha, right? Misha Doller from Ericsson, who is the head of the Ericsson research, and they're really promoting this Internet of Touch, like smell, another sense of ours, right? And Internet of Skills as a result of that. Because if you can replicate, let's say I'm a surgeon, I'm not skillful in my hand. If I was, and if you can replicate the skill set here at another point, then that may yield an outstanding surgeon at various locations, right? So this is another way of creating remote, online, real-time surgery. So that's an ongoing field. So what are the emerging IoBNT applications, like organs on chips or various biomedical applications? So can we actually create organs on the electronic environment? Or can we actually create diseases on the electronic or chip or integrated circuit environment? And the answer is yes. People are already working on this. And why? The reason is obvious. Otherwise, you have to use animal models to test the drugs or to test the diseases or test the diagnosis techniques or grow some organs to do all these tests, right? Why not? Why don't we do it on an IC, on an integrated circuit, right? So this is a very important emerging research field. So what is in relation to IoBNT? Well, again, come back to our bodies. None of the organs or cells or tissues work alone. They always communicate, right? So these organs on chip need to also communicate. So they need to have these communication modalities, whether molecular or electrochemical communications or electronic or electromagnetic communications, doesn't matter, or acoustic. So they should have all these communication capabilities. So as an artifact of this field, we can talk about Internet of Organoids. So that's is an emerging, a very new interdisciplinary emerging field. So basically communication between organoids. So what is organoid? Similar to the organs on a chip, but it's a broader naming for that. It's a self-organizing and three-dimensional tissues. They resemble the primary structural, functional, and biological complexity of an organ, the actual original organ, and they typically derive from the stem cells. So basically, you generate the three-dimensional tissue which replicate the primary structure and the functionalities of the original organ. You may not necessarily grow the entire organ. If we can do it, that's perfect, right? We can, replace our heart or kidney, etc. But this is the first step towards that end. In fact, here, like there's a professor whose name is Madeleine Lancaster. Maybe you can invite her sometimes for the presentation, who are actually growing the brainoids. They could be used, instead of animal models, they could be used for drug testing or testing for the diagnosis or treatment methodologies. So, of course, there are many uses, but it's not easy to grow them. I mean, speaking is easy, but actually doing that it takes time, and most of the time it fails. But when you have it, we can also work on the communication capabilities. For the time being, we're trying to come up with correct interfaces and practical communication techniques, which we can actually embed to the organoids so that we can realize this broader organ on chip or networked organoid vision. Once we have it, we will collaborate. We will continue collaborating. Obviously, we're actually collaborating, but not in the physical testbed sense for the time being. Then try and validate our results. What we envision right now is three modalities. Molecular, obviously, that is the native communication approach in that territory, as we have discussed previously. So they may be through gap junctions or neurotransmitters, vesicles, or signaling molecules, or even charged ions. And optogenetic communication might be another alternative or option. We can easily embed light-sensitive proteins in the organoids and use them as an interface to trigger some, signaling, or use them to transduce some signaling. This is a happening modality. This is existing, but we're considering to incorporate it into organoids. And ultrasonic-based communications, basically acoustic, which is well studied in the biomedical setting. I think it would be easier to do this compared to these two options. Obviously, there are many challenges. Nothing new compared to others that we have mentioned. I've mentioned in the broader IoE. Biocompatibility is an issue, miniaturization. The actual platform, the actual physical infrastructure that you can create this connection or interfacing, and security and privacy, again, understudied, estimated, and we also don't work on this field. Again, many enabling technologies, neural interfaces, and it exists. Very good research outcomes exist in this field. Optical sensing, imaging, and optogenetic is a growing field, so we can learn from those research areas. So I skip these a bit faster. And what we are trying to do is to bring all these research artifacts, let's say, to come up with communication solutions for organoids. And this is the 4-level roadmap for Internet of Organoids. Obviously, have the organoid culture in a standardized manner and integrated with sensor technologies. I know, saying it easy, and have the connectivity established, and ultimately get the data and do some analysis through different algorithms. Okay. Let me move towards the plans, and then I'll touch upon the space, and I'll wrap up hopefully over the next 15 minutes or so. I hope I'm doing fine in terms of time. Otherwise, let me know. I can speed up. So Internet of Agricultural Things.
10 minutes, Özgür.
Okay, perfect. So Internet of Agricultural Things is one of the conventional fields in the IoE. I'm not going to go into details. Obviously, the idea is to automate the agriculture using the devices. And there are many nice technologies like the cowlers, using the cows as the sensors roaming in the field, and smart tractors and drones, etc. So this is fine, and people are calling it like Internet of Food and Farm. But what we're more interested in is whether can we get the plants on board as communicating entities. In fact, they're already doing it. So Internet of Plants, with another term, Wood Wide Web, existing. So this is the term that other researchers have given. Again, don't shoot the messenger. So what's happening here is that plants have been observed to communicate intentionally. So one example here is that when this guy is infected or infested by some insects, so this releases certain chemicals and signals the adjacent one through these mycorrhizal links. Mycorrhizal means using the common fungi interface to the root of the flower or of the plant. And then this guy, knowing this attack, will release certain defense volatile organic compounds to repel the incoming attack. Okay, so this is one of the signaling mechanisms of Internet of Plants. So I strongly recommend you to check this book from Dr. Merlin Sheldrake, who is an alumni from Cambridge Engineering Department as well, who studied entangled life of the fungi and talks about communication. That's very fascinating, by the way. So how many modalities of the Internet of Plants exist in the nature? 4 for the time being, as we know of. There might be others. Who knows? Quantum might be there as well. Chemical signaling, mycorrhizal communication. This is through the fungi. Chemical is through the leaves or through the flowers. Basic molecular communication, airborne, through volatile organic compounds. Electrical signaling, interesting. I'm going to show you some videos if the time permits, and acoustic communications. So in terms of the territory, you can consider it like above ground and below ground. So and they have different challenges in terms of channel environments as well. So you need to focus on those when you study, of course. You can see this meanwhile. So what's happening here, when you actually stimulate one flower here, you can see the response on the other one. So there is no direct connection between these two flowers. So this is the electrical communication. There has been many experimental studies. You can check the literature. We don't know the details. We know how this is actually happening. We know the mechanism, but we don't know why and how. We can speculate all day, but this is worth to study. Acoustic communication, on the other hand, is very interesting. Plants emit sounds, very interesting. So I'm going to click on this. Maybe you can hear the sound of a tomato plant, or I will hear, I don't know. Let me know if you can hear or not. Oops, didn't work. Anyways, no worries. You can check this paper and find it online. They have already shared this. Basically, recording of the tomato plant sound has been obtained. Okay, they respond to certain stress. My personal communication, as I've mentioned, through the fungi attached to the roots of the plants have been also physically observed through imaging techniques. You can find that. So these are not speculation, by the way, but needs to be studied from our perspective, ICT perspective. So for that, we've just received a new project funded by TÜBİTAK, it's a national NSF, to study all these different modalities of communication inside the farm, basically. So we've been working on this from the perspective of energy harvesting in the Internet of Plants. So very interesting domain. Some of the plants can be used as an agent to actually coordinate and modulate the energy harvesting in the farm to optimize the use of the resources. And we've been mathematically modeling the stress communication between the plants. Basically, once one plant is induced a certain type of a stress, biotic or abiotic stress, then it releases volatile organic compounds. Basically, it tries to communicate airborne, and you can see the output of the stress at the other plant, at the other end of the channel. So this channel, this communication is worthwhile to study as well. Interesting work, still under review, how the plants actually detect and process the sound waves and leading to physiological response. So this is an ongoing work, very fascinating. I'll be happy to share the paper with you as well. I'm going fast forward. Last few minutes, I guess 6 minutes of my time on the space. I know I have taken from very small scale, now talking about this crazy stuff on the space, but that was my intention. So what's happening in the space? So initially it was thought, the space was thought for internet. So we could use the space and satellite systems to, improve the internet. And then name was different, Internet for Space. It was during my PhD time. We were working on this, funded by NASA under the supervision of Professor Akildes. And it was called like delay tolerant networking or interplanetary internet. Then the naming of this changed to Internet of Planets. Nowadays, over the last 10 years or so, it's called Internet of Space. In fact, this has been coined by SpaceX and IEEE at the same time. So this is like the cumulative network of all the entities regarding the planet. So conventional things happening, I'm not going to go into details, like RF optical communications at the satellites and at the space shuttles and space stations at these different bands, which is classical stuff. An emerging field here is to apply terahertz in the space setting. Very nice work happening in this direction. One emerging or hot subfield is basically what's going to happen in terms of the ISAC, like Internet of Sensing and Communications, let's say on the surface of the Mars or on the surface of the Moon, using, for example, terahertz, or around the Earth, for example, for the detection of debris, right? Because the satellites get blown up and there's a huge debris around the Earth orbit, right? Or can we actually do like dust storm sensing at the same time communicating with the rovers and the orbit around the Mars? And can we do this with terahertz in the Mars? Because as you know, terahertz is not advantages on the surface of the Earth because of the absorbance by the oxygen and water molecules, but no such thing happens in the vacuum in the space. Another adverse effect exists on the Mars atmosphere, but not as unfriendly as on the Earth atmosphere. So these are conventional stuff happening. Some unconventional stuff is an ongoing research. We're not working on this, but some researchers are, mostly in the US, is called neutrino communication. So neutrino, as you know, is a chargeless particle, and theoretically speaking, you can generate them and transmit from any point in the universe to another without any problem, because since they are chargeless, they won't be affected by any electrical or magnetic field. So this picture is not an illustration. You can see the engineer here with a hat, and this is the neutrino receiver. Okay, so you cannot attach it to your iPhone for the time being, but people are trying to make this small scale and make the generator also small scale. The problem with the neutrino communication for the time being is the generation. It's not stable, and its coherence is limited. But even though in 2012 there has been a physical experiment and they've realized very reliable communication with neutrino particles. Okay, so you may want to look at this direction. So the bottom line that I wanted to mention here is the gravity. You know, gravity exists. I don't need to convince you. I don't have much time to go into details of that for the time being, but feel free to read our very detailed tutorial paper on the gravitational communications. Basically, the idea is that gravity is one of the important phenomena, physical phenomena, which affects the universe. There are different aspects of this in the different scales that has been studied both theoretically and experimentally. And gravitational waves have been actually experimentally observed very recently. Very recently means like 10 years ago, right, in 2015. But compared to when they've been articulated by Einstein and his predecessors, like almost more than half century ago, then 10 years ago is very recently. And it's been shown that the gravitational wave exist, which means that when you have, let's say, one way of generating the wave, thankfully not the only way, if you have two black holes, and if you can collide them, you can actually change the space-time curvature. And this modulation on the space-time curvature can be detected by certain receivers. So LIGO is one of those. Okay, so this is laser interferometer gravitational wave observatory, LIGO experiment, has been done in the US in 2015 and has detected first gravitational wave. But its amplitude, its magnitude and amplitude is very limited. Okay, you cannot actually do communication with that. Okay, I'm contradicting with myself, but theoretically speaking, you can do anything as long as there is a propagation or transmission of a wave or energy. So there are different ways of creating gravitational wave. You can even do it in your room through rotating bar and piezoelectric material. Like there are mechanical techniques, there are superconducting methods, there are high energy methods. Again, I don't go into details, but this paper explains all of these very nicely. But the amplitudes here are extremely small and very difficult to detect. And there are detection methods, direct or indirect. The direct method, LIGO, has been used in that experiment. Indirect methods are easier to generate, but less capable in detecting. Basically, indirect detection methods are transducer, as in our communication terminology. Okay? So you can say, why are we talking about this? You can even do gravitational wave modulation. Well, black holes do that naturally, but when you generate the gravitational wave, you can do AM modulation, you can do frequency modulation, as in our sense, FM, and you can do superconductor modulation, which could be considered as like phase modulation, the type of a phase modulation. So what type of a channel we have here? We're working on it, and I know other groups are also working on it. We have some model right now, but we need to work on it, and hopefully we will share the results very soon. There are even patents. I've just shared one here. There are very brave souls out there and crazier souls out there, like communication system using gravitational waves. And there is this very long way ahead for the gravitational wave communication in the Internet of Space. But this is one of the frontiers in the new Internet of Everything landscape. So this concludes my a little bit long speech. I would like to thank you again, Professor Akyildiz, for this invitation. I'm honored, and I'm most grateful to you. And I would like to thank all of my students who have actually helped with the presentation and done the presentation slides, actually, because I was sick, and for all their great work so far. Thank you very much.
Thank you, Özgür. Excellent talk, and you gave a very global overview about the entire field. I enjoyed listening to you. But when we look at the entire area, and somebody from outside will, I mean, I was one of you guys, listen to us, they miss the connection to the technology transfer. In other words, let me give you some examples. Maybe you missed those, or maybe I missed them. So there are, for example, when you use them for health applications, right? So then when you have these synthetic molecules or nanoparticles, they have some immune response problems, right? Toxicity. And
Right.
also engineered bacteria could mutate or disrupt microbiome balance. So that
Yeah.
also, as you know, that the current biosensors lack sensitivity and specificity for real-time molecular decoding. So when you look at all these cases, also molecular signal degradation, so in other words, when we have this bridge from this theory that the last, say, 15 years or maybe 18 years, we have been doing all of this. So this bridge is somehow not attacked by the researchers. Maybe you do that, but in this talk, somehow you did not present them. You covered everything, what is happening from the theoretical perspective and doing all this research. These are excellent and solid research. But some people may say, what about the applications? In other words, if I want to use this technology, for example, you talked about plants, right? And I'm sure Bige, who was also your student, will be very sad that you somehow forgot her paper. It was published in Transaction Nanobioscience for plant pheromones in 2016, almost 10 years ago. But now
Oh,
what
yeah.
happened is we
I know the
left,
paper. Yeah.
we did end-to-end channel model.
Yeah.
Then we said, okay, there's, long way to go for the technology transfer. So now people, because I'm working with Indian UK company, they are doing agricultural engineering. So what can we do to help them as an example? So you do basic research, but at the end of the day, they would like to see how can I use this technology. So you want to add some of your opinions?
Yeah, Professor Akyildiz, this is you are absolutely right. I mean, this is really missing in the entire field. Definitely missing in my work.
No,
So
Özgür, this is not criticism, please.
no.
I'm not.
Yeah, I know. Yeah.
This is excellent work, really. Please don't ever
No, I
think
know.
that.
Well, thank
But
you.
I'm
Yeah, I
talking
know.
about people that, because it happened to me too. So when I
Yeah.
present this basic research, they always attack me.
Yeah.
But it's not between you and me. It's not attack. But I'm just saying
Yeah.
that isn't it time that we should try to show that bridge and help these people?
Exactly. I think time even has passed. It's like two-way. So we have to do our own responsibilities. Basically, we have to keep that in mind more in when we do our research. This transaction is necessary. Otherwise, it will never take off. You're absolutely right, right? They will be all nice pieces of papers, etc., but then it won't actually touch people's lives. So at the end of the day, that's what we do, why we do research, right? So we have to do our own duty to that end. And we have to also work maybe to get more like industry people and companies more and more on board so that they are interested in collaborating. So that's I was trying to say I missed that. I kind of failed that. I tried to
No,
the
no,
best
but
of my capabilities so far. I mean, I
Özgür,
touched some companies, etc., but it was difficult. So maybe that part is missing. But definitely,
you
you are
should,
right. We have to do
first
that.
of all, you are not late. Second, you are still young. Third is
Thank you.
this is still excellent time to do it, you know, so don't get
Yeah,
frustrated.
yeah. No,
So
you're right. You're
also,
absolutely right.
you know, I recommend you to work with people like Chris Contact. Remember, we were working with
Yeah,
him
of
here
course,
in
of
Norway
course.
time, so
Yeah,
that they can help us for the, you know, especially health applications, because your
exactly.
research is excellent, you know, and on the
Thank you,
of
Professor.
course, yeah, of course, come on. But then, you know, people, and also you can do that. That's why I have full trust in you that you can do that
Thank you.
technology transfer. Some people cannot, you know, but you can. And so that's why. Another issue is
All
that
right.
I'm having the same problem, maybe you too. There are some people, they are attacking me in the background about ethical issues. I hope it doesn't happen to you, that there are these paranoias that we are doing these things, that we are trying to poison the world. I'm serious.
Yeah,
So I hope it's not happening to you, but I assume it does. So we have
yeah,
to also teach these people that what we are doing is really helping the mankind, you know. It's not just
yeah.
for
Yeah,
right?
exactly. I mean, you're definitely right. I receive these questions as well. I mean, they attack through the ethical aspect, or they attack through the privacy security aspect. You know, what are you going to do when you connect my brain or when you connect my kidney? I'm telling you, I don't have such intentions, or none of the people doing this research have such intention. Of course, when we come up with any engineering solution or science, it could be used for good or bad, right? We know from the Manhattan Project example, or anything of that sort. So, but on the other hand, I'm having difficulty in answering those questions, giving examples of ongoing research on the ethical or privacy security aspects of the field as well. So maybe when that aspect, that dimension of the field grows more and more, we might be more equipped with
But
stronger answers to
Özgür, I
counter
don't
that.
think it's our domain or our responsibility to
Yeah, of
think about
course.
those. We are
No,
engineers and scientists, you know, we cannot
yeah,
get into those and let the other strategies
of
and
course.
policy holders do that,
It,
lawyers do it.
exactly. I mean, that's
So
always the case with wireless as well. There's always, even with
exactly,
classical wireless,
exactly.
there are bad
Ex-
usages of that as well, right? Ethical and some other.
Yeah, they were saying that wireless communication causes cancer and brain tumors. Remember when you were in my lab.
Exactly, exactly. I
So
remember that. Yeah.
Carlos Diaz Araujo says that thank you, Professor Özgür, for this excellent, powerful presentation. And he wants to have your presentation slides to share. Maybe he can contact you directly, and you know we can
So,
solve the question between yourselves. Umur Alp, I'm sure you know him too.
yeah, I know.
And he sends you greetings, and he says, "Do you think terrestrial and aquatic plants?" I think he's talking about maybe algae.
Yeah,
That's also a very hot topic, by the way. I am
yeah.
working on it. Really.
I'm not surprised. Yeah,
You will see that soon. So,
sure.
aquatic plants exhibit different communication mechanisms, such as underwater magnetic signaling.
Well, very good question. I don't have any direct answer. I would say just yes. I mean, I would imagine, because there are different channel environments, and they may have evolved in using different types of modalities, and very exciting direction. I'm not surprised that you will be leading that field as well. But yeah, definitely. Umrab, sorry, because I haven't studied the plants underwater, but yeah. That's another word. I
Good
would
area.
expect that. Yeah, very good area. I would
That's
expect they
right.
will be using something else. Yeah, very good
I
question.
think, unfortunately, there are no more questions, but honestly, I have to say, not because you're my son or whatever, it was excellent as usual. And
Thank you,
I
Professor.
knew that. And you gave an excellent overview presentation, and I'm sure it will motivate a lot of young people to conduct research on this topic. And we will put this on the YouTube and also on social media. I'm sure that will trigger many, many research ideas by other young people. So thanks a lot, really, for this outstanding presentation. Alessia, you can take over and ask him your questions.
Thank
Thank you.
you. Thank you
Thank you
very
very much,
much.
Professor Akil.
Thank you,
Once again,
Professor
I'm
Figi.
honored to be here. Thank you so
Thank you.
much.
Thanks a lot for your excellent presentation, Professor Akan. And now let's move to the Wisdom Corner. So live life lessons, which aims at offering a unique special angle to this series of webinars, adding a personal touch. So I would start with my first question to you. Looking back on your journey, what is the most valuable life lesson or even a failure that you have encountered that shaped your path, and how can this lesson inspire or guide those attending the webinar?
Okay, there are many, of course, some involving Professor Akil, as you can also imagine. Wow. Well, thank you very much for this question.
Özgür, I have nothing to do with those questions.
That's fine. Okay,
Please,
yeah,
honestly.
that's fine. Yeah,
Alessia
okay.
hides them. So really.
That's fine, no worries. Uh, I mean, I have so many such milestones or events that I remember in my life in the past that shaped this journey, right? So that's what you have asked. So this journey has of course, started with the childhood and then high school, etc., as everyone else, but then it actually has taken off uh, uh, by my PhD. Because until then, I didn't know. I had applied PhD, but it was just because I didn't like my job at the time, honestly. Okay, and I wanted to do PhD because I felt like I'm not utilizing my prior background in maths and physics, etc. And I didn't enjoy doing, engineering in the company that I was working. And I had some experience with some papers with my prior supervisor in masters. It was also very helpful, Professor Birman Baykal. And then I sent email, I remember, to Professor Akildis, and I wasn't expecting any response. We're talking about 2002, by the way, because he was like one of the gods at the time in the field, and I was, of course, no one. I thought I had some papers, but then I learned that they were not really papers. Anyways, he said uh, at the time, again, I should elaborate this a little bit to my young colleagues. Maybe we didn't have any Zoom or Skype or anything at all, just plain email. That was the best technology. Anyways, so he replied immediately, and he always replies immediately. He said, let's, do you have these and that, etc. And then he said, I'm going to hire you. And then I flew to Atlanta. I had a connection in New York, and there was a snow in Atlanta, and I think it has never snowed afterwards. And then I said, oh my God, I have to stay in the airport. Should I really continue? And I was hearing, many unfriendly things. Are you sure you're coming to this group, etc.? You're crazy. Why are you doing this, etc.? And my father was in the hospital at the time, and I was stuck in the airport. I had some money. I called the agency in Ankara, Turkey, saying that, look, I'm coming back. Can you buy me a ticket back home? And they were trying to do this, and then there was an announcement. Okay, the flight is taken off from New York to Atlanta. And a friend of mine at the time, Professor Tuna Tucu, right now he's a professor at another university in Turkey. taken me from the airport and said, now we will go and meet with the professor. I said, okay. And I went to professor and, you know, I was, of course, very excited and nervous. And he was very crystal clear as to what I should do and what is expecting of me in this journey. He said, we have a progress meeting in 2 days or 3 days. I don't exactly remember because I think it was Tuesday and we used to have progress meetings on Friday. Your project, your topic is next generation wireless or wireless internet. This is the project that you're funded. Get ready and work hard, and I'll see you on Friday. I said, okay, this is another game. So forget everything that you learned so far, Özgür. So at the time when you're young, you feel like, well, you're on top of everything. You're like the next generation Einstein or whatnot. Of course, you're not. I skipped
I
some
jump in?
details, Professor.
Please.
Can I jump in? This guy was number 80 out of 1.5 million participants for the examination into the universities of Turkey. So
Oh,
he was
wow.
one of the top guys. So he didn't mention because he's too friendly. I told him, look, if you don't perform, you will be out.
Yeah, I skipped those parts. Yeah, he said exactly that with a
I can imagine.
clearer language, as you can imagine. I
Yeah.
said, okay, now that's the thing. And then, I had to learn my room, and I was taken to supermarket that said to learn everything and prepare for the progress report and work the game. I always try to be ahead of what I would be asked for, and since then I was trying to follow this first lesson and all of the other priceless lessons that I've learned in my PhD. I mean, that's basically what shapes any researcher. That's what I have experienced, That's the thing. Because there's no textbook of how you can learn, how you do research, or how you can become a professor, etc. You just learn this from, master and apprenticeship type of relation from your advisor. So that's why I
Sure.
told at the beginning I'm indebted to Professor. Yeah.
Thank you. Thanks for sharing your first experience also with Professor Akilditz. I would
Yeah.
ask you, what key advice would you give to young professionals or aspiring to build a career in academia and or research? In your experience, what essential skills and qualities contribute most to success in these fields?
Yeah. Yeah, very good question and very difficult question, one. For me, again, that's why you're asking my opinion. I think that's the attitude. Like, again, you should never say that, yeah, you know everything and you're better than everyone. That's not the case, okay? Experience is everything. If there is a PhD advisor, you have to trust that person. They've been through many things before you, okay? But use your logic and use your positive attitude and resilience. There will be always failure. I mean, I've failed my first submissions. No need to mention one being the Infocom, my first submission, rejected. Another one rejected. That rejections, of course, that's life, right? Don't worry about it. You will get rejected, but get up and work harder. I think work hard, and enjoy. If you don't enjoy it, you won't be successful. Again, if I may, I will refer to, I never forget, to the protocol, because we were dealing with protocols with Professor Akildis. His protocol was HIP-T. Maybe I remember this was mentioned in prior webinar series as well, here as well. You need to be hardworking, really. You need to have the integrity. Otherwise, it will come out. It's a long journey. It's not just few days or few years until you get your PhD. No. And you have to be persistent. So this is HIP. And he had a dash, then talent. Talent, of course, you need to be talented, but yeah, it's some sort of material property. We can say it like intrinsic material property, but you can improve your talent as well. Like you need to work hard to improve your talent again. And then you will be successful, definitely. And don't try to follow the crowd. Just trust yourself, be confident in yourself. Don't say, yeah, everyone is working on this. Now I'm going to work on that. So that's also what I learned from professor, my advisor, not this, do it the other way around, don't follow the crowd. Just follow your own self. If you do
Very
something
nice.
meaningful, then at some point people may follow you or not. That's not the point, right?
Yeah.
But
Yeah.
do whatever you want to do. So I think these are all I can say.
Yeah. Excellent advice. Thank you so much. And what first inspired your passion for your field? And how did you turn this interest into an important career?
A very, very good question. I mean, it, it, I'm not coming from the rich background. Okay, I realized very early on that I had to work hard, and I'm not skillful in my hands or sports or whatnot. I realized I can do something with my, head. And in my high school, which was a science high school, I was a mathematics Olympiad student, and I was in
Mm,
national Olympiads, etc. And I was not really a fan of physics. I was into maths. And
mhm,
in the undergrads, in electrical engineering, there are basically two sides. Some people go into physics side of it, like devices and circuits. Some people go to mathematics, like communications and signal processing. There I realized I'm a communications person. So I like it. And I think communications is one of the most important and paramount inventions of human being. We need it, and nature is also using it. So there is always new things to do in this field. So I tried to do something in masters while I was trying to do in my work, but then I realized, as I mentioned, that's not really communication. It's just configuring some routers, etc. But again, with my first initial failures and then propelling that I received by the motivation from my PhD advisor in my PhD, I realized and I've become confident in myself that I can actually turn this into something. I don't know. I mean, honestly, professor said at the beginning very nice things about me. I'm really honored and humbled, but I don't feel like myself that I've achieved. I mean, I've done something, but you understand what I'm saying. So I think there's a lot more to do.
But actually, among your career achievements, my last question, is there one
Yeah.
particular contribution that has had a profound impact on you or others? And what makes this accomplishment especially meaningful to you?
Yeah, very good one. I remember one. I'm sure there are many. Honestly, I haven't studied these questions. So I might be answering wrong, maybe suboptimal. But
There's no
anyway,
wrong
I
answer.
know, I know. Thank you. So I'm sure there might be many that I could pick, but I remember one which we have really worked and tried hard, which was the first work that we tried to model the nervous system using communication theory. And we submitted the same paper 3 times to IEEE Transactions and Communications, all rejected. And it has taken 4.5 years for us to get that eventually accepted. And I have never given up. During that time, I was trying to write, proposals for, funding, national and international on this field. And they were also all rejected.
Mm,
And at the same time, I had proposed one new course in my prior institution in Ankara on this molecular communications and nervous system, etc. And it was rejected. They said, "Oh, come on, this is crazy. Come on." And that paper got accepted, and my co-author, yeah, it was published in 2013 or 14 in IEEE Transactions on Communications. Same year, I received ERC grant. same year, previous year and same year, I received twice IBM Faculty Awards in the same field. And the same co-author of mine, I mean, my PhD, my master's students then, is now a professor at my prior institution teaching this topic. So it's like interesting, touching to several pieces. So I really feel proud of this.
Absolutely. Oh yeah. Ian.
Thank you again, Özgür. In fact,
thank you, Professor.
We still have people here, and I would like to repeat what you said. Actually, this is good news that you still believe that you did not achieve what you want to achieve, because that hunger will continue to perform. Because when you reach that maximum, then the life is over, meaning you're done. So look how old I am, and I'm still trying, right? So because that's the feeling you have. So that's life, which is good. You should be happy and never ever lose that, please. Okay. And
I'll do my best, Professor. Thank you.
Yeah, I always told you that, you should. Plus, never ever be 100% happy in life. Because if you're totally happy, then life is over. So we discussed those things, right? I'm just telling the young people. So you have to always strive for better and better and achieve more, but in an honest way. That's what you do, all integrity and honest way. And thank you again, Özgür, and especially I'm very touched that you recognize my efforts for you in the beginning. Of course, after that,
always
you took off yourself, so it's fantastic. Thank you. And Alessia,
thank you very much.
My dear Alessia,
thank you
again. It was very nice as always, Erika and Maria. So we'll see you next week. We have another excellent speaker, and enjoy the evening. So
thank you so much. Thank you so much, Professor Akan. It was really a pleasure. Thank you.
Thank you so much.
Thank you,
once
everybody.
again.
Thank
you.
you.
I'm honored.
Thank you. Bye-bye.
Thank you.
Bye-bye.